Again, hopefully you got that periodic table handy. We're gonna need that for the charges of the binary ions here in a moment. And hopefully you got that paper that has the polyatomic ions on it. Nomenclature. Nomenclature is a system for naming different compounds and taking a look at a compound's chemical formula and getting its name out of that. Now, formulas can take on multiple different forms. There's an empirical formula, which we'll talk about probably tomorrow night. I just can't even believe that. And then structural formula, and we get into Lewis structures. But right now, we're looking at what are called the molecular formula. This gives you the exact composition of the substance. Excuse me. Come on, boys, hang in there. It gives you the exact composition of the substance. So we'll talk about the difference between empirical and structural tomorrow. You may say, why do we need nomenclature? What is nomenclature? What's the point of nomenclature? Well, nomenclature is the division of chemistry that is dedicated to naming chemical compounds. It is a system. It's essentially a language. Why is chemistry so darn hard? Well, there's stuff to memorize, there's math, and it's got its own language. That's a recipe for one tough thing. I can't think of any other subject that's got math, stuff you got to memorize, and a language built into it. But whatever. I mean, biology just stole Latin. It's not even its own language. Chemists invented their own language. That's how crazy we are. The amazing thing is that the language is incredibly efficient. So I'm getting a little ahead of myself. Why do we need to invent our own language? Well, nomenclature did not always exist. Chemical nomenclature used to just be memorizing the couple hundred unique names for the few compounds that had been discovered. So before Thompson and Rutherford and people started figuring out, oh my God, there's more compounds out there than we thought. People used to, like chemists, used to just memorize a unique name for everything. So there were like maybe 200, 300, 400 compounds, and they all had unique names. Some of those names are still around. Epsom salts, milk of magnesia, gypsum, laughing gas. The problem is once we started realizing how many compounds there were out there, you cannot memorize a unique name for every compound on Earth. We are now over 5 million. So there have been more than 5 million unique chemical compounds that have been discovered or created. You can't memorize 5 million unique names. Now, I will say of the 5 million, a lot of those are organic. So you're going to have to take organic chemistry to learn, a couple million of them. But a lot of them are ionic and covalent. So elements that don't, or elements can say nonmetals that don't have carbon in them. Those are covalent compounds, have carbon as their backbone. So we're going to be able to name all of the substances, hopefully after tonight, except for the organic ones. So we're going to start out with binary ionic nomenclature, talk about type 2 metal nomenclature, talk about nomenclature with polyatomic ions. And then we'll get into covalent nomenclature, which is easy. And then we'll do acid-base nomenclature to close it out for the night. So we're acid nomenclature to close it out for the night. So let's do this thing. First thing, this harkens back to what we were talking about at the beginning of class. Two different kinds of compounds, ionic and covalent, and you got to be able to identify them based on the types of atoms that are in them. Now, we are going to talk about ionic versus covalent quite a bit when we get to our Lewis structure bonding unit. But right now, we're just going to focus on how to name them. So here's our periodic table. Here's our staircase. Metals over here, except for hydrogen. Non-metals over here. Okay. If a compound is ionic, it's got a metal and a non-metal. Something from here, something from here. If a compound is covalent or molecular, both terms are fine with me. I don't care. Some people are picky. If a compound is covalent or molecular, it contains only nonmetals. So non-metal plus non-metal. We are going to name these different compounds completely differently. Covalent molecular compounds, they're going to get prefixes. This is where we use mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, that's coming. That's later. We're going to start with ionic. Ionic nomenclature is way more difficult. Ionic nomenclature has got stuff to memorize. You got to do a little bit of math to get the charges to cancel out and make a neutral compound. It's tougher. So we're starting with the tougher one, where we got metals and we got nonmetals. We're going to start with the simplest type of ionic compound first, which is a binary ionic compound. Binary ionic compound contains one metal and one type of metal and one type of nonmetal. Okay, so let's get to it. So how do we name binary ionic compounds? It's pretty easy. If you have a binary ionic compound, you name the metal, and then you change the ending of the nonmetal to "ide." So for example, chlorine becomes chloride, and then that's how we would name it. Now, what we are going to do here first is we are going to go from formula to name. Okay, it is far more difficult to go from name to formula because then you have to worry about getting charges to cancel out. So let's look at an example. We got to talk about charges, but we're going to start here with the easy stuff, going from formula to name. So NaCl. We recognize that this is a ionic compound. How do I know it's ionic? Well, sodium's over here, chlorine's over here, some from the left, some from the right, ionic. Binary ionic, one kind of metal, one kind of non-metal. So this is gonna, what do? We name the metal, that's just sodium. And then chlorine becomes chloride. Now, my guess is you already knew that was sodium chloride, right? Let's do another one, CaO. Again, we know this is ionic because we've got a metal and we got a non-metal. So we name the metal calcium, and oxygen becomes oxide. Now, when you name binary ionic compounds, if there is a subscript denoting that you have more than one element, you ignore it. So, for example, when I name this ionic compound, so again, we got a metal, and we got a non-metal. When I name this ionic compound, I just name the metal, magnesium. And I don't care that there's two bromines. I don't care. The bromine goes to bromide, magnesium, bromide. Now we'll talk about why that 2 is there in a minute. That 2 is there to balance out the charge. I'm going to need 2 bromides to balance out the charge of that magnesium. We're going to get to charges here in a second. But when you go from formula to name, it is just super easy. I'll give you another example. Let's do K3N. We name that. I ignore the fact there's 3 potassiums. I don't care. That's just potassium. And then nitrogen becomes nitride. Potassium nitride. Let's try this. Okay, I want you to name, we already did number 1. I want you to do 2 to 6 because we already did number 1. Try 2 to 6, name those compounds. Go ahead. Hopefully, you guys got potassium iodide. Over here, you got calcium sulfide, lithium nitride, cesium, or as the British would say, Cal, this is for you, cesium bromide. They also say aluminium instead of aluminum, and francium instead of francium. Tomato. And then magnesium oxide. Any questions on 2 through 6 there? Okay, potassium iodide, calcium sulfide, lithium nitride, cesium bromide, and magnesium oxide. How are we feeling about those? So it is easy, hopefully, to go from formula to name. But now we need to talk about, why do some of these have subscripts in there? What's going on with that? And this gets into charge. Here we go. Now, it's always difficult to talk about charges of these ions before we've done the bonding unit and the quantum mechanics unit to understand the idea behind the octet rule. But we're going to introduce that right now. The chemical properties of an atom come from the number of electrons that are in its outer energy level. They're called valence electrons. And we haven't gotten to that unit yet, but we got to be able to name compounds. So I'm going to give you the quick rundown on valence electrons. It's easy to determine the number of valence electrons for the main group elements, and the main group elements just don't count the transition metals here. The transition metals are going to behave differently. Many of them have multiple charges. They're going to be type 2 metals. Oh my goodness, we'll get there. Hang in there. But the easy way to get the number of valence electrons for the atoms is to number cross 1 to 8, skipping the transition metals. So 1, 2, 3, 4, 5, 6, 7, and 8. And in fact, there's an A numbering system, 1A, 2A, 3A, 4A, that does this. That tells you how many valence electrons the atoms have. There's actually only one exception. Helium only has 2. I told you before, hydrogen and helium, they don't have a good spot on the periodic table. Again, eventually when it's up to me, and someday it will be, I would move hydrogen and helium off of the table. Anyway, so this is how many valence electrons the atoms have. You may know some properties of the noble gases already. The noble gases are ridiculously stable, and their stability comes from having 8 valence electrons. So neon, argon, krypton, xenon, radon, they are ridiculously stable. And all of the other elements are like super jealous of them. They also want to have 8 valence electrons around them. So what they do is they gain and lose electrons to try to get to that magic number of 8. And metals are going to go about that differently than the non-metals. So if we put our staircase back on here, the metals, okay, are not very close to 8. So if we think about like lithium only has 1 valence electron. It would have to try to gain 7. Lithium would need to become a -7 anion. That is not going to happen. That is too far away. Nobody's going to give lithium 7 electrons. So what the metals do is the metals are actually losers. Okay. Metals don't try to gain electrons. They just give up. The metals say, listen, I'm not anywhere close to 8. So instead of trying to gain electrons to look like a noble gas, I'm going to give away my valence electrons. And then I'm going to go backwards to looking like the previous noble gas. When you have the same electronic configuration as something else, it's called being isoelectronic. We will get there, chapter 6. Okay. So what do the metals do? Well, if you're sodium and you only have 1 valence electron, what sodium does is it just gives it away. And when sodium gives away that 1 valence electron, it goes from having 11 total to 10 total. You know what is 10 total? Neon. So what happens is when the metals give away their electrons, they go backwards and look like the previous noble gas, okay? And they become isoelectronic with the noble gas that came before it. So what everybody in the alkali metal family does, right? So I'm using that term. We just got the name of the families tonight. Okay, if we look at the alkali metals, again, hydrogen doesn't count. These guys all have 1 valence electron. They all form +1 cations. I would write that down on your periodic table. Now, you should memorize that. You need to be able to know how to get that. But all the elements in column 1 form +1 cations because they all like to give away 1 electron to go backwards to looking like a noble gas. The alkaline earth metals, let's pick strontium, for example. Strontium's got 2 valence electrons. Well, it wants to get to 8. It's 6 away. Things are not looking good. Unless you say, well, wait a minute, instead of trying to gain 6, what if strontium gives away those 2? And that's exactly what it does. Strontium gives away all of its valence electrons. It goes from having 38 total to 36, and now it's back to looking like krypton. So the whole alkaline earth metal family, group 2, these guys all form +2 cations. Now, these other metals, hang in there. We won't talk about them. Most of them are type 2 metal cations that have multiple charges. There are a couple that I want to just mention right now that you should memorize. Scandium is always +3. Write that down. What else? Let's see. Zinc and cadmium, these two, they are always +2. And then gold and silver, these two, they almost always like to be +1. These guys like to be +1. Now, gold can be +3 sometimes, but most of the time it's rocking the +1 charge. I don't really consider it to be a typical type 2 metal. Okay, cool. So there's your metals. We'll get
I'm
to
sorry,
all.
one question. On the left you wrote, like on the left top you wrote +1. What does that +1 represent?
That's the charge that it likes to
Okay,
have.
the
Also,
part.
Kristen said, are we supposed to see your screen? I should be sharing my screen right now. Do you guys not see a periodic table with some numbers? Because
We do,
that would be crappy. What's that?
we do see it, yes.
So these are the charges that the elements like to take on. So lithium likes to be +1. Sodium likes to be +1, right? Potassium likes to have a +1 charge when it forms an ionic compound. Okay, these guys all like to be +1. The alkaline earth metals all like to be +2. So if barium's in an ionic compound, barium is going to be +2. Right? So you can predict the charges using this method that I'm trying to show you. You'll see how we're going to use those charges in a moment, but that's what that +1 means. It means this whole family likes to be +1. Does that make sense?
Yes, thank you.
So that's the metals. Metals are losers. They give away electrons, they take on a positive charge. Let's talk about non-metals. Non-metals, okay, they are gainers. Non-metals like to gain electrons. Why? They're closer to having 8, so they don't give up. Instead of giving up and giving away electrons, they're going to gain them. So for example, let's talk about my favorite family of elements. Hopefully you guys remember the name already. This is the halogens. The halogens have 7 valence electrons. They are so close to 8, right? If you're an atom, the meaning of life is like finding, what is that, nirvana, right? Finding inner peace is having 8 valence electrons. Your driving force in life is to get a full octet in your outer energy shell. So the halogens are like right there, man. They all have 7 valence electrons. So the halogens all form -1 anions. So fluoride likes to have a -1 charge, chloride, bromide, iodide, acetate. Okay, they all like to be -1. Okay, oxygen's family, as you could figure out, because they have 6 valence electrons, they need 2 more. This whole family is going to become a -2. These guys are going to have a -2 charge when they're in an ionic compound. Nitrogen's family is going to have a -3 charge. And then carbon and silicon's family is special. Carbon and silicon, this is why organic chemistry exists. Okay, carbon has a valency of 4. It's got 4 valence electrons. So what that means is it can gain 4 and lose 4. It's kind of in the middle. So that's why it has a totally, carbon does not do ionic. Okay, it does its own thing, right? Oh, I forgot to mention aluminum likes to be +3. Obviously, it's got 3 valence electrons, so it's going to give away the 3. And remember, aluminum is not a metalloid, or is not a metalloid or semi-metal. It's a metal, and it's a metal that likes to have a +3 charge. There's another one that has a set charge. So what do we have? Hopefully on your periodic table, you got some charges written. You've got the alkali metals like to be +1, the alkaline earth metals like to be +2. You got scandium's +3, silver and gold +1, zinc and cadmium +2, aluminum +3. Hopefully over here at the non-metals, you got that the halogens are -1, the oxygen family likes to have a -2 charge, the nitrogen family atoms like to have a -3 charge. Hopefully you got that. And now what we're going to do is we're going to take this new information we just got, and we're going to use that to create neutral chemical compounds. Now I'm hoping you got at least binary ionic formula writing in high school, but you never know. So hopefully you got that periodic table out in front of you. We're going to do a couple. We're going to put some of these cats and kittens together, and we're going to predict formulas from names, and this is when it starts to get to the next level. Your goal when writing ionic formulas is to combine the cations and anions so that their charges cancel out and you have a neutral compound. That's the name of the game, ladies and gentlemen. When you take an ionic name and turn it into a formula, you are bringing the ions together to create a neutral compound. Sometimes it's really easy. You jam them together all willy-nilly. They cancel each other out perfectly. Sometimes it's far more difficult. Let's look at an easy one. Lithium bromide. Here I have the name. I want to write the formula. You need to have a periodic table out in front of you. And we need to find lithium. Take a look at the periodic table. It's like a scavenger hunt. You will find lithium in group 1. Lithium is an alkali metal. If this is the first time you have ever done this, I highly encourage you to show your work. Like, actually write down what I'm about to do. If you had a strong high school chemistry background and you can do this in your head, I am all about that. But you got to figure out which one of those two camps you fall in. So lithium, if you find that on the periodic table, lithium is a group 1 metal. And lithium, when it forms an ionic compound, likes to have a +1 charge. Now we need to find bromine, right? Because bromide is bromine with a -1 charge. So if we find bromine, bromine is a halogen. And bromine, because it has 7 valence electrons, that whole family likes to have a -1 charge. Well, this is the perfect scenario, folks. We're taking a +1 cation and a -1 anion. How do I bring them together and make a neutral compound? I just go is lithium bromide. Their charges cancel out perfectly. Lithium has a +1, bromide has a -1. They're going to come together in a 1-to-1 ratio to create lithium bromide, which is a neutral compound. It's not always +1, -1, for example. Let's do barium sulfide. So like a scavenger hunt, you got to find barium on the periodic table. Barium is an alkaline metal. It's group 2, which means barium likes to have a +2 charge. If you are just starting out with this, you should be writing that down. If we find sulfur, sulfur is an oxygen spin. Sulfur has 6 valence electrons. It needs to gain 2 to get to 8. So sulfide is going to be sulfur with a -2 charge. How do I bring barium sulfide together, barium and sulfur together to make a neutral ionic compound barium sulfide? I just jam them together again because that's +2 and that's -2. They cancel each other out. It's perfect BAS. So sometimes you get lucky and they just go straight together. Most of the time, that doesn't happen. Let's try to write the formula for calcium fluoride. Take your periodic table, find calcium. Calcium has got a +2 charge. It's an alkaline metal, 2 valence electrons, gives them away, +2 charge. Fluoride, if you find fluoride is the king of the halogens. It's at the top. They have 7 valence electrons. They need 1 more to look like a noble gas. So fluoride is going to be F -1. Now I cannot jam them together all willy-nilly. A +2 charge and a -1 charge, not going to work. So what do I need to do? Well, if this guy's +2 and this guy's -1, I'm going to need two of these guys to cancel that out and create a neutral 0 charge. Think about it. +2, -1. I'm going to need two of these. That's -2 now. If I have two of them, each one's -1. If each one's -1 and I got two of them, that's a total in -2. They're going to cancel out. Calcium fluoride is now CaF2. And we write that 2 down here as a subscript. That subscript denotes the number of elements. You cannot write it at the top. If you write it like in line with it, that's where we write coefficients, which tells us the number of molecules, which we're going to do when we get to balancing. Okay, so it just goes on there as a subscript. I'll give you another one. How about sodium oxide? Find sodium. Write down its symbol and charge. Find oxide. Write down its symbol and charge. Try and bring them together and make a neutral compound. Go ahead. All right. Sodium, an alkali metal, likes to rock the +1 charge. Oxide likes to rock a -2 charge. I can't jam them together all willy-nilly. +1, -2 doesn't cancel out. I need two sodiums. That's Na2O. I got a bunch more for you to practice. Let's practice writing the formula for numbers 7 to 12. Give 7 to 12 a shot. I want you to write the formula for 7 to 12. You got this, folks. All right, folks. Here we go. You stop me if you got questions, all right? Sodium iodide. Sodium rocks the +1 charge. Iodide rocks the -1 charge. Sodium iodide is just NaI. Magnesium. Magnesium's an alkaline earth metal, got a +2 charge. Fluoride's a halogen, got a -1 charge. That's going to be MgCl2. You only need two fluorides to cancel that out. Potassium's got a +1 charge. It's an alkaline metal. The oxide's -2. I'm going to need two potassiums. That's a K2O to cancel out that -2 charge. Cesium's an alkali metal. It's got a +1 charge. Fluoride's a halogen. It's got a -1 charge. That's a match made in heaven, ladies and gentlemen. That's just CSF. Aluminum or aluminium, that's got a +3 charge, right? Bromide, that's got a -1 charge. I'm going to need 3 bromides to cancel out that aluminum, right? 3 of them. That's AlBr3. Barium sulfide. Barium's an alkaline earth metal. It's got a +2 charge. Sulfide's a member of oxygen's family. It's got a -2 charge. So they go together great. BAS. I think we did that one earlier anyway. How'd we do 7 to 12, folks? How'd we do? Hopefully you did that in high school. If you didn't, what were you doing in high school, right? I mean, but boy, I've taught chemistry at a couple schools now. It's not the same at every place, you know? How? Because it's going to get 10,000 times harder than this, right? But this is the simple binary stuff. Okay, let's talk about type 2 metal ions, folks. Oh, yeah, this is where it starts to get good. Okay. So when we're talking about metals, the alkali metals are +1, the alkaline earth metals are +2, aluminum's +3, and then a couple of these guys have set charges, like scandium's +3, zinc and cadmium are +2 always, silver and gold are usually always +1. But what about these other guys? What about like iron and cobalt and nickel and copper and like chromium, and what about tin and lead and antimony, and like what is going on with these other guys, right? And even uranium, and like what are their charges, right? The answer is they're not set. Okay, their charges, they can have multiple charges. They can have more than one charge. For example, iron can be +2 or +3, cobalt can be +2 or +3, nickel can be +2 or +3, copper can be +1 or +2, lead can be +2 or +4, tin can be +2 or +4, antimony can be +3 or +5. Manganese can be anywhere from +1 to +7, +1, +2, +3, +4. Its charges are all over the place. This stuff gets nuts. Metals that can have more than one charge are called type 2 metals. I got good news for you. When I was in high school, such a long time ago, uh, they were still using the Latin form of nomenclature. And you had to memorize the Latin names for these ions. I think I am the last generation of chemists that have to memorize the Latin. So, for example, iron with a +2 charge is called ferrous. Iron with a +3 charge is called ferric. Cobaltus, cobaltic, nickelus, nickelic, cupros, cupric, let's see, stannous, stannic, plumbus, plumbic, antimonus, antimonic, chromus, chromic. Okay, the ion with the lower charge ends in us, and we use the Latin. And the ion with the higher charge ends in ic. But that system isn't great because it only works if the atom has two different ions. What if it has like five? What do you do then? It gets crazy. Luckily for you, okay, although I am a little angry and bitter about it, luckily for you, they've gotten rid of the Latin and they've moved to a Roman numeral system. So type 2 metals, write this on the board now. You don't need to know the Latin system. I will tell you this. If any of you are thinking about going on to be a chemist, which it doesn't sound like, if I remember correctly from last night, what you guys said you wanted to do, it didn't sound like anybody was saying, oh, I want to go do research in a lab. But if you do end up becoming a chemist, you do kind of have to learn the Latin. The reason for that is some reagents are shelf stable for like indefinitely. So if I walk into work tomorrow or I walk into Hack, okay, there's going to be a bottle of plumbus nitrate on the shelf, okay, because plumbus nitrate doesn't really, there's going to be a bottle, it's from like 1985, right? So if you end up working in a lab, you're going to run across the Latin. You kind of got to learn it anyway.